And last time we were talking about some kind of a tough question of, we've talked about linear approximations, and we've basically made an argument that says that, it seems like a function, that we should be able to be approximated by a first degree polynomial. And if it is possible to approximate it by a first degree polynomial, it kind of has to be this thing here that we wrote down a formula for. But it doesn't address the question of how do we know that something actually can be well approximated by a first degree polynomial. We just assumed that, right? And said, well, if this linear approximation exists. Right? So now we're going to kind of address the question of, but when does this work, and does it always work? And by the way, no, it doesn't always work. These kinds of nastier issues. So I'm just going to hit the kind of the broad strokes of the argument. The way that we address this, because it is a little bit formal, and it's more formal than Math 219 focuses on. But at the same time, I think you do need to understand what it is that we are avoiding by the methods that we're going to develop. Okay, so here we go. Let's look at this function right here. Now, this is a weird function, admittedly, but perfectly fine as a function. Oh, wait, we already talked about this part, didn't we? Yeah, we already did this part. Am I right? Okay, so the big idea here was that this function, weird function, technically it is defined at the origin, and the gradient is defined at the origin in the sense that it's made up of partials that are perfectly well defined, and yet the resulting linear approximation is kind of preposterous, right? It's not even close to a good approximation for lots and lots of points that are very, very close to the origin. So this is not good. Anything that we write down for this function should not be called a linear approximation. Okay, so what is it that went wrong? I ask rhetorically, and I'm going to say, in some sense, I feel like the error is not going to zero is really the problem. So, for example, if I approach the origin from kind of the first quadrant, let me just switch to here. Okay, so if I approach the origin from the first quadrant like that, well, the value of the function is 0, but this linear approximation, the value of the linear approximation up there is 1. Right? So, as I get closer and closer to the origin, the actual values of the function are 0. These approximations, as I do the same thing, are 1. And that error, the difference between the approximated value and the actual value, that difference, our error, stays large all the way toward the origin. So I'm going to define the error to be that difference, right? The actual value of the function minus the approximated value of the function, the candidate approximated value of the function. And surely the fact that this error is not approaching 0 is at least part of the problem. Question though, is this the entire problem? And I say that no. This is actually not the entire problem. It's not going to be sufficient to just require error to go to 0. And here's my example of why it's not good enough. Let's consider this next function. Now, this is back to single variable, you'll notice. This single variable calculus, right? Here is a function, and here is an approximation. I'm going to call this a candidate, candidate approximation. And is this a good linear approximation? Well, no. Come on. That's ridiculous. I mean, at a casual glance, you can see this is obviously not a good linear approximation of this, in fact, a linear function, right? Obviously, the linear approximation should be, well, the function itself in this case. But what's actually wrong with this as a linear approximation? If you look at the error, right, the error is the difference of these values. Those errors, as you get closer and closer to 0, those errors get smaller and smaller, and the limit of those errors is in fact, 0. So if we were to show up somewhere and say, hey, I think this orange function is a good linear approximation of that green function, because, hey, check it out, the error goes to 0, that's a pretty weak argument and a pretty wrong conclusion. I think it's pretty satisfying to see that this is a bad conclusion here. Okay, so this idea that we should just have error approaching 0 does not cut it. It is not good enough. And here's how we're going to fix it. We're going to define this better thing called relative error. The idea of relative error is to acknowledge that how far off you are just doesn't tell the whole story. We need to know how far off are you compared to how far away are you from the point where you're doing your approximations. And the closer you are, the closer those approximations really ought to be, right? So we're going to divide, and this is just a construction. We're going to divide how far off your estimate is by how far away is your input point from the approximation point. And I'm going to propose not only should the error approach 0, but furthermore, this relative error should also approach 0. Now let's apply this stronger criterion to the same exact example we were looking at a minute ago. So again, we were looking at this function here, 5x. There's the graph of that function. Here's my candidate approximation that kind of laughably passed our first test, right? Which is poor test. But here's that function. And now let's think about what is the relative error, and does that relative error approach 0? Well, the relative error is the difference between the actual value and the estimated value, but then divided by how far off are we from where we're doing the estimate, namely x minus a. And if you plug in for what these things are, we know all of the functions involved, and we have formulas for everything in that expression, and that limit, this relative error, does not approach 0. So as is appropriate, this candidate linear approximation has failed our test, thankfully, right? It should fail. It's obviously not a good linear approximation. So what we've got now is a test that as it should, correctly rejects bad linear approximations. So the way we phrase this, we call this vanishing relative error. The idea vanishing means that it's approaching 0. Relative error, of course, is what we defined above. So this is the criterion that we need to define what it means to have a good linear approximation. And I'm just going to write that down, and there's a bunch of notation to talk about here. But relative error, here it is. Relative error is defined by this formula right here. Again, it's error divided by distance you are away from the input. Error, don't forget, is actual value minus estimated value. Estimated value, don't forget, is, it's our linear approximation formula. It's this thing right here. And I do have a parentheses problem. I'm going to distribute the minus in the parentheses there by turning that minus into a plus. So relative error, if you kind of stretch it all out and write down what is the formula for it, it's this great big monstrosity here. And I need for my relative error, namely all of this great big monstrosity, I need that to approach 0 as you approach your point of estimation. So this is the definition of what we call differentiability. This is what it means to have a function that is truly well approximated by its linear approximation. Said differently, this is what it means for a function to have a good linear approximation. Now, it's just a definition. The motivation for this definition is all this talk up here. There's a lot more that we could say about this if this were Math 222 instead of Math 219. And for Math 219, I don't think it's a good choice of time to to spend much more time in this. But I wanted you to know, ballpark, why do people write down this great big monstrous expression? What does that have to do with anything? And, where does it come from? Okay. All right. So now real quick, I'm also going to point out a little bit of terminology. If you look at the error, whoops, wrong color. If you look at our error here, we previously thought of that as actual value of the function minus estimated value of the function. But now instead, notice I can move the kind of the grouping around a little bit. I can rewrite that as actual change in the value of the function minus estimated change in the value of the function. And these are things that we will be talking about. So this is just an opportunity for me to introduce these words. I should use a different color. There. This thing here is called the increment. Increment means the actual change in the value of the function. And this thing over here is our linear estimate of that increment. And of course, y'all may recall linear estimates of changes is what we mean when we say the word differential. Right? A differential is a linear estimate of how much something changed. So this is literally that estimate. Okay, so heads up on that terminology. Okay. Question, rhetorical question. Are you telling me that anytime I want to do a linear approximation, if I want to justify that my linear approximation is actually a reasonable linear approximation, you telling me that I've got to deal with this great big thing and take the limit, the multivariable, mind you, limit as x approaches 8? We didn't even cover the section on multivariable limits in this class, right? We kind of skipped over that part. We just, not going to really come up very much. Wouldn't that be a bummer if every time we wanted to do a linear approximation and actually, claim that anything good from it, that we had to deal with all of this? So good news, we don't. There's a very powerful tool that we can use to kind of circumvent all of this, and it's called continuous differentiability. So here's the definition. A function is continuously differentiable if two things. Take the partial derivatives and then check one, make sure that the partial derivatives exist where you're interested in talking about continuous differentiability. Make sure that they exist, make sure there's no divide by zero or, something like that. And make sure that they're continuous. Right? Make sure they exist, make sure they're continuous. Very easy to check. All you have to do is compute partials, world's easiest derivatives. Confirm that nothing explodes. Confirm that they are in one of the many large categories of functions that we already know are continuous. All polynomials are continuous. All exponentials, logs and trig functions, where they're defined, are continuous. Right? All this is all kind of stealing from single variable calculus. But usually at a glance, you can just look and see that, a function's a known continuous function. And once you know that a function is continuously differentiable, you can cite this theorem that says if your function is continuously differentiable, then it follows immediately from this result. That function is differentiable. That function satisfies this test. This monstrosity does indeed approach zero. You don't have to deal with the monstrosity. You get to just conclude what you need from it by just checking continuous differentiability, which again is easy. Let me show you an example. All right, so looking at this function right here, and we ask, is this function differentiable? Oh, golly. At a glance, again, if you were to take this question at face value, well, you would have to go back up to here, write down the monstrosity, take the multivariable limit as x approaches a, and after computing that, confirm that indeed we got zero. And again, we don't even know how to do that. That's the face value approach. The clever, much more convenient way to do this is to cite the above theorem and say, look, You've asked about differentiability. I'm going to take it a step further and ask the stronger question, is this continuously differentiable? And, well, we take the partials. In fact, you don't even have to compute the partials. At a glance, I can see these are polynomials. All the partials are going to be polynomials. Polynomials are known, continuous functions. So my partials exist and are continuous. My function is continuously differentiable, and therefore my function is differentiable. Didn't have to deal with any limits, didn't have to deal with any monstrosity fractions, nothing. Everybody good? So in practice, day in and day out, this is how we confirm differentiability. There is a downside, there is a cost. There are some functions that are kind of what you might call in between these two definitions. There are some functions that technically are differentiable, but they aren't continuously differentiable. So you can't use continuous differentiability if the function doesn't have continuous differentiability, right? And in those cases, golly, then you got to deal with the monstrosity on the previous page. Good news, that's not going to come up in Math 219. And it doesn't come up in the real world very much either. Okay. All right. So here's another useful fact. I guess I should come back up here real quick. Notice that this theorem here only allows you to conclude that a function is differentiable. This doesn't give you anything that you could check from which you can conclude, and therefore the function is not differentiable. It just doesn't do that. But here's another true fact. Every differentiable function is continuous. And if you turn that around backwards in what we call the contrapositive, I hope everybody remembers that from at some point in your past. Do y'all remember the contrapositive construction? Some of you are nodding yes. Okay. The contrapositive says if you've got a statement P implies Q, well, then if Q ends up being false, well then P must have been false also. Right? So think about it in this context. What would happen if a function's not continuous? Could that function that is not continuous, could it be differentiable? Could it be differentiable? Let's think about it. If the function were differentiable, then it would also be continuous, but it can't be because it's known, it's by assumption not continuous. So it's just not possible for the function to be differentiable, and therefore we conclude the function is not differentiable. So this is another nice test, and this is what we can use in this case here. You'll recall this strange piecewise defined function here from last time, and visibly not continuous, right? And because it's not continuous, we can conclude that it is not differentiable. Is that cool? All right. Okie dokie. So we're going to move on now and talk about the derivative. A lot of what I have on the next 2 pages is just kind of rephrasing stuff we've already talked about. So I'm going to go a little quickly on this. It's largely, in fact, just terminology that we're covering here. But I do think it's important to explicitly rephrase this as I'm about to rephrase it so that we can get a close-up look on exactly what this DF matrix is all about. What we have written previously was the linear approximation formula. Right? This we wrote down several pages back, and this is, in some sense, if there is going to be a linear approximation, it kind of has to be this, because this is the only function that has all the right partial derivatives. It's just this is the only candidate. One of the deals, though, with linear approximations is at the point where you're doing your approximation, the linear estimate has to equal to the actual value of the function. That's one of its jobs. L's job is to mimic F. So at the point A, of course, it's got to have the right value. Then I can take this and move it over to the other side, and notice what I've got now. You look at this form. The left-hand side of the equation is now literally the output differential. It's our linear estimate of how much the function changes. L of x minus L of a. It's not the increment. It's not f of x minus f of a. It's the differential. It's our linear estimate of how much the function's changing. And on the right-hand side, of course, x minus a, well, that's just the change in the input. That's our input differential. So check it out then, what our DF matrix is doing. Our DF matrix here, and I kind of like looking at it down here instead, same thing. Our DF matrix is a relationship between input changes and output changes. And if you recall the very first thing that we said about derivatives, I promised that, there's going to be a bunch of different derivatives in this class. And by the way, we've kind of already seen a bunch of different derivatives. Partial derivatives, the gradient vector is kind of a derivative in its way. We've got this DF matrix thing. It's made up of a bunch of derivatives. Plays a role kind of like a derivative, right? We've got several different kinds of derivatives. And this one, this thing DF, is really the most general of them. It, again, turns input changes like dx, input changes into output changes, aka df. So it is a kind of a derivative. And in fact, this is what mathematicians are usually talking about when they say the derivative. If you're talking about a vector-valued multivariable function, the derivative, in the most general sense, let's not make any assumptions about, it has to be real valued or anything like that. In the fully general sense, the thing that turns input changes, which are vectors, into output changes, which are also vectors, is this matrix. So that's the derivative. And this is a little bit of a weird thing to digest first time you see it. In Calc 1, the derivative is always a number. Right? You take some function, you take its derivative, you evaluate that derivative at a given point, it's a number, a scalar value. So we're kind of psychologically accustomed to thinking of the derivative as being a scalar valued thing, as being a number, in other words. Here it's not. In multivariable calculus, when you talk about the derivative, not a derivative or something, a kind of a derivative, but you talk about the derivative, it's a matrix. So it's a change of category in the multivariable context. So a little weird, something to digest, something to think about. This is sometimes explicitly noted in the language. Sometimes we call it, just to make it clear what we're doing, the derivative matrix, to remove possible ambiguity of maybe we're talking about one of these other kinds of derivatives. So derivative matrix is a pretty common term. Of course, matrices are linear transformations, and sometimes people like to say the derivative transformation. That's just another way to think about what a matrix is as a linear transformation. Okay. And to further confuse things with terminology, sometimes the DF is written as JF. J stands for Jacobian. So sometimes this is called the Jacobian matrix, named after a mathematician named Jacobi. Anyway, along those lines, the J instead of the D. So you'll see all of these different terms and both of these different notations to refer to this one thing, which, again, deep down, what it is that this is what derivatives are in a multivariable context. Okay. How are we doing? Let me pause for a second. I've been talking a lot here. Is everybody happy? Everybody following? All right, let me draw a picture of this. Again, the derivative matrix turns input changes into output changes. Let's actually see that in the picture here. So we've got a domain. We've got a target. Keep in mind what a function is. A function takes input points in the domain, and returns to you output points in the target. All right, so the function f goes from the domain to the target. So let's think about what df does. Again, df doesn't turn a point A into a point f of A. df turns a input change, namely a vector, like a displacement in the domain, into the corresponding output change, namely our linear estimate of the resulting change in the output value of the function. So it doesn't take points to points, it takes vectors to vectors. Everybody see the difference there? All right. Now, related, I'll point out that you can take this equation right here. Well, let me go to purple. You can take this equation right here and just kind of divide both sides of the equation by dt, and I'm deliberately being sloppy about this because as far as we're concerned, this is fine. Nothing to worry about here. Skipping some formalities. But dividing by dt, I can now reinterpret the equation as saying, let's see here, I'll do this. Yeah, here we go. I can reinterpret this equation as saying that what the derivative matrix does is it turns input velocities, not changes, but rates of change, into output velocities. Again, rate of change. So the derivative matrix turns that velocity vector into that velocity vector. So nice interpretation. Then you can think of the derivative as, again, it turns input changes into output changes. They can be discrete changes like in this first equation, or it can be instantaneous rates of change as in this second equation. Take your pick depending on your application. We know what's going on in the problem at hand. Either of these is fair. Okay. Alrighty. Now, another, this is just a notational alternative. You may recall that we also wrote this formula back here for the case of real valued functions, where m is 1. We wrote this with the gradient in this position instead of the derivative matrix. Right? It was gradient dot x minus a instead of df matrix times, matrix times x minus a. So, what's the difference and why, which of those should I use, you might ask? Well, here's the thing. Notice that if you're doing dot products with a gradient vector, that's morally equivalent to multiplying by the df matrix. After all, if you're talking about a real valued function, the df matrix only has one row. There's only one output. Outputs correspond to rows. So there's only one row. And let's look and see what's inside of this one row. Well, it's all the partials of the function f with respect to all the input variables. That's what the gradient is. The only difference, when you're talking about a real valued function, the only difference between the gradient vector and the derivative matrix is that we think of the gradient vector as being written vertically, and we think of the derivative matrix as being written horizontally. It's the same elements, though, just kind of written sideways. So these are actually the same things. In other words, I don't have to reinterpret. I don't have to choose whether should I use the gradient or should I use the derivative matrix. For a real valued function where you can use either, they're literally the same formulas, just written with a different notation. Okay. So, interpreting, though, in this context, thinking of the derivative as being executed by a gradient vector, thinking of it as a dot product with a gradient vector instead of as a matrix, then the gradient vector is the thing that turns input changes into output changes. It plays the same role that the derivative does, just you have to use the dot product because it's a vector. Is that okay to everybody? Any questions? Everybody's good? Okay, so we're going to talk about higher order partial derivatives now. I'm going to start off with just a few general properties of differentiation. I do want to make a distinction about the difference between a derivative and the act of differentiation, a little bit different. here's the derivative. Again, the derivative is a matrix. What do matrices do? Matrices multiply by vectors and return other vectors. So a matrix is a function from Euclidean space to Euclidean space, right? Depending on how many inputs and outputs, Rn to Rm. All right, that's what a derivative does. Now I want to, by contrast, I want to talk about not the whole df. I want to talk about just d. D I'm going to think of as being the act of differentiation. What does the act of differentiation do? Well, the act of differentiation turns a function f into a matrix df. Right, that's what differentiation does. You come in with a multivariable function. Taking its derivative means I'm going to take that function and do certain calculations, and out will come the derivative matrix df. So a little bit of a weird thing to think about. I mean, we're much more accustomed to thinking of functions from Rn to Rm, right? Nice Euclidean space. Everything's kind of convenient and relatable. Here, though, we have a function from this abstract vector space of differentiable functions, right? This is an infinite dimensional vector space, right? Into this other kind of, I don't know, semi-abstract vector space consisting of matrices. And think back to Math 218 and you can confirm for yourselves that these are in fact vector spaces. Okay, so the assertion that I'm making here is that this D is linear. And I emphasize, I'm not saying DF is linear. DF, of course it's linear. DF is a matrix. All matrices are linear. That's not what we're saying here. We're making a new statement that D, the act of differentiation, is linear. So said differently, when you put a linear combination in to the act of differentiation, you get a linear combination out of those individual derivatives. Okay, so differentiation is linear. Let me show you an explicit example. Get some numbers on the page. Here we have a couple of functions. These are multivariable vector valued functions, right? We can take their derivatives. No big deal. Here's the derivative of the first function. Here's the derivative of the second function. Now, while we're here, let me remind you, make sure that you remember the formulas for how to compute these derivative matrices. It's very important. And in particular, be very careful to remember which numbers go where. It's really easy to accidentally transpose, right? And this happens a lot on exams, and it's catastrophically, I mean, it's importantly wrong and will lead to catastrophically bad answers. So do make sure not to accidentally transpose. Don't get these backwards. Again, very dangerous. Okay, so I've taken their derivatives, but now let's look at a linear combination of these functions, right? So here I've got f and g, and if I take this linear combination of those functions, I get a new function h, which y'all can multiply out these functions. It's just a matter of multiplying the first one by 5, second one by 6, add them up, and you get this function right here. So now I've got a couple of things I can compute. Keep in mind the linearity assertion is that if I do a linear combination of those derivative matrices, or if I were to find a new derivative matrix of the linear combination of those functions, that I should get the same thing either way. So let's check that out and see if that worked. Well, here's a linear combination of the matrices. Right, you can see I'm taking the individual derivative matrices and taking the linear combination. Here you might say I'm taking the linear combination after differentiating. Over here, I'm taking the linear combination before differentiating. Right, and of course now I've got that function right there, and I've computed its derivative matrix. So there you go. This is the derivative of the combination. This is the combination of the derivatives. These are the two things that we need to be equal if we're going to confirm linearity. And sure enough, as desired, these are equal, which tracks with the idea that this is a linear process. Is everybody with me? All right, a couple other things. These are easily read in the book. There's various versions of product rule, quotient rule for multivariable vector-valued functions. And there's different versions about, oh gosh, well, are you taking the dot product of two vector-valued functions? Are you taking a scalar-valued function and multiplying by a vector-valued function? There's different kinds of products that you can talk about for vector-valued and scalar-valued functions. So there are various different product rules, quotient rule, etc. So these are in the book. They're highly readable. I do think it's a healthy exercise for you to pick one and confirm by direct computation. Crank it out. Right? Write it out in coordinates. Compute both sides. Confirm that, yeah, sure enough, they are actually equal. Like I say, a healthy exercise, and I hope you'll take the time and maybe do one. Let's say at least one of those. If you have trouble with the first one, try a second one. But easily confirmed, and again in the book. And so I'm not going to spend class time again. Math 219. It moves so fast. I have to make tough choices, and this didn't make the cut for class time. But I emphasize this is fair game, and so make sure to read that part of the textbook. And I'm going to move on now and talk about higher order partials. So y'all remember single variable higher order partials, higher order derivatives. You can talk about the second derivative or the third derivative in a Calc 1 class, right? And they have nice geometric interpretations, etc. So, okay, can you do the same thing for multivariable functions and partial derivatives? And why, yes, you can. Because, after all, if you have a function of several variables, f, when you take its partial derivative with respect to something, the result is still a function of several variables, all those same several variables. And so you can talk about its partials. So here, as an example, function of two variables, I can take its x partial or its y partial. No big deal. And we've talked about these notations, and so we're already good down to that point, right? Notice, as I just claimed, the reason that I can compute the x or y partial of this function is because it's a function of x and y. Well, let's look at our partials, and they too are functions of x and y. So I can talk about their partials just as well. That's really the same idea. So looking at this x partial, for example, well, I can talk about the x partial of that x partial. Or I could talk about the y partial of that x partial. That's what we call a mixed partial. All right, so let's talk about the notation a little bit. Unfortunately, there's some awkwardness in the notation for a couple of reasons. So again, let's start off with that we're looking at the x partial and we're taking the y partial of it. Well, here's our existing notation for the x partial, and here is our existing notation for how I take the y partial of whatever it is I'm taking a y partial of. And so this particular second partial, you can see the motivation for writing the notation like this. And, it's a little bit sloppy in a way, right? I mean, we've got the partial symbol seemingly squared. It's not that the partial symbol represents a real number that's being multiplied by itself. That's not what it is, right? So this squared notation here is not really squared. It's just a convenient representation of the fact that there's two partial symbols here. That's all it is. So don't get bogged down in the fact that that notation seems suggestive of something that doesn't make sense. Likewise, you see in the denominators here, kind of makes sense to write these like that. Okay. All right. Now, here's another notational alternative. The x partial is alternatively written f sub x. taking the y partial of something is alternatively denoted as having a y subscript. And you could probably see how we'd be motivated to rewrite this in this way. We got f that's got an x subscript, and there's a following y subscript. Well, shouldn't we call that fxy? And that's all well and good, except for the fact that I'm sure you've noticed that depending on which notation you're using, which partial happens first is either on the right or on the left, depending on which of the notations. And so that's a little annoying, and it's unavoidable given the notational choices that we have here. So it just kind of is what it is. So I'm just going to call that a notational landmine to be aware of, and you can't get around it. So there you go. All right. Okay, so now, of course, likewise up here, you can talk about the y partial, and you can talk about taking the x partial of that y partial, or you could take the y partial of that y partial. And, algebra, and you can compute. What I think is interesting to note here is that the y partial of the x partial and the x partial of the y partial happen to be the same here for this function. Right? Now, did I have to contrive that? Did I have to manufacture carefully to make this work out? And it turns out that no, this is not a coincidence. This is, in fact, usually the case, in some sense. So, as follows. Now, I do have to, there's a little aside here to talk about exactly when this works. So, this, bear with me, we just have to define a term here. We've got this thing called CK. This is a vector space. This is a special vector space. Gets used a lot in analysis kind of stuff, such as multivariate calculus. So CK is a collection of functions. It's a vector space of functions. The K refers to how many partials of it you have to be able to take. And the C represents the fact that all of those partials have to be continuous. All right, so CK represents functions that are not only continuous themselves, but where up to and including its kth order partials also all continuous. So this is what we call a regularity condition. A function that is CK is a nice function, and the higher K is, the nicer it is, the smoother, and the more you can do with it without running into any nasty problems. All right, so here's the punchline. Getting back up here to mixed partials, and when are mixed partials equal, independent of rearranging the order of the partials? The answer is as long as your functions are CK. Right? If your function is CK, then you can look at any mixed partial of K partial derivatives. You can rearrange however you like. So notice the same K for both of these. Right? Rearrange however as long as these are all the same numbers, just in different orders. Right? As long as, in other words, these are all the same partials that you're taking. You just kind of change the order that you're doing the partials. If your function is CK, then those mixed partials, as expected, are always equal. Is that all right? Now, I'm not going to prove this. By the way, this is very hard, well beyond Math 219 to be able to prove. Okay. All right. So, nice little bit of good news. Let's think about a little bit of geometry here. What do second partial derivatives look like? We're going to restrict the discussion to graphs. Again, I remind you have to be very careful when you're talking about geometric interpretations of things. What something looks like in a level set context, on the level set picture, very, very, very different from what it looks like on a graph picture. So here we're going to talk just about graphs. And we start with some good news. If you're talking about the unmixed second partials, like fxx, for example. So we're taking the x partial of the x partial. Right? That's exactly what you think it is. for the purpose of both of these derivatives, both of these partial derivatives, y is being treated as a constant. That means that for the purposes of the entire calculation of fxx, y is a constant. So we're just looking at this cross section, and we're just looking just at this curve. That one cross section. And what are we doing to that curve? Well, we're taking literally its second derivative. So, it means exactly the same thing that it means in single variable calculus. In this case, concave down means second x partial is negative, just like in single variable calculus. Negative second partial means concave down. Right. And likewise, for the purposes of this calculation here, doing fyy, notice x is constant for both of those partials. And so we're looking in this cross-section, the cross-section of which looks like that. And what are we doing to that cross-section function? Well, we're taking its second derivative. Second derivative means, negative is concave down, positive is concave up. So this one's concave up, so that's y second partial positive. So exactly what you would think. And things do get weirder, though, when we look at mixed second partials. And this is a longer conversation. I want to lead into this, though, with how hard it is to talk about this by pointing out that even though we can make a geometric interpretation of this y partial, taking a y partial of a function f, I can talk about the graph of f, right? We've been talking about graphs of functions and what a partial derivatives look like for a little while now. And y partials say, as you're moving in the y direction, find the corresponding tangent line to the surface and look at the slope of that tangent line to that graph. That's what the y partial means. Problem, though, if I then say, how do I make sense out of the x partial? Again, if you want to interpret an x partial as a slope, you need to be looking at a graph of the thing you're taking the x partial of, and I don't have that. Right? The thing I'm taking the x partial of is partial of f with respect to y. I don't have a graph of that. I kind of have a suggestive kind of a picture maybe, but this, in terms of how this communicates to me about the y partial of f, this is not the graph of the y partial of f. It's the graph of just f. Right? So I can't interpret this x partial in terms of slopes. What I can do is I can interpret this x partial as, as I move in the x direction, how does that, whatever that thing is I'm taking the x partial of, how does that thing change as I move in that y direction? So what we're going to talk about next time on Monday is how would I make sense out of this picture of keeping track of the y partials in this direction, and how are those y partials in that direction changing as I move in the x direction like this. Y'all have a good weekend. Go Duke!